Article 310.15b6 of the National Electrical Code provides specific guidelines for sizing service entrance conductors for dwelling units. It's important to understand the limitations and proper application of this article. The question specifically pertains to whether you can install parallel 350 aluminum feeders with a 4/0 neutral on the line side of the meter. The answer to this question is no. The reason for this lies in the proper application of the National Electrical Code, specifically regarding conductor ampacity and neutral sizing. Article 310.15b6 provides reduced ampacity for service conductors under certain conditions, specifically for dwelling units. However, this allowance does not extend to all situations, particularly when conductors are paralleled. When conductors are run in parallel, each conductor must be sized to carry its proportionate share of the total load. The overcurrent protection device must also be sized accordingly. In this scenario, using parallel 350 aluminum conductors might seem like a way to achieve the necessary ampacity for 300 amp service, but the neutral conductor must also be properly sized. The National Electrical Code mandates that the neutral conductor be sized based on the maximum unbalanced load. This load is determined by considering the types of loads connected to the system. For dwelling units, the neutral conductor typically needs to carry the maximum current that will flow on it. In the case of a 300 amp service, the neutral conductor must be capable of carrying a significant portion of that current, especially if there are substantial nonlinear loads present such as electronic devices, LED lighting, and other modern appliances. These nonlinear loads generate harmonic currents, which can significantly increase the current flowing on the neutral conductor. These harmonic currents can lead to overheating of the neutral conductor if it is not adequately sized. A 4/0 neutral conductor may not be sufficient to handle the unbalanced load and harmonic currents associated with a 300 amp service, especially when paralleled conductors are used. Furthermore, the allowance provided by Article 310.15b6 does not override the general requirements for neutral conductor sizing outlined in other sections of the National Electrical Code, such as Article 220.61, which deals with optional calculation for dwelling unit loads. This section requires the neutral conductor to be sized based on the calculated load, taking into account various demand factors. In summary, while Article 310.15b6 allows for reduced ampacity of service entrance conductors under specific circumstances, it does not permit undersized neutral conductors. The neutral conductor must always be sized to carry the maximum unbalanced load, including any harmonic currents that may be present. Using a 4/0 neutral with parallel 350 aluminum conductors on a 300 amp service is unlikely to meet the requirements of the National Electrical Code and could pose a safety hazard. It's always recommended to consult with a qualified electrical engineer or inspector to ensure that all electrical installations comply with the applicable codes and standards. Additional considerations involve voltage drop. When conductors are run over long distances, voltage drop can become a significant issue. Undersized conductors can lead to excessive voltage drop, which can negatively impact the performance of electrical equipment. To mitigate voltage drop, it may be necessary to use larger conductors than what is strictly required for ampacity. Furthermore, the installation of paralleled conductors must comply with specific requirements outlined in the National Electrical Code. These requirements include ensuring that all conductors are of the same material, same size, same length, and installed in the same raceway or cable. This is to ensure that the current is evenly distributed among the paralleled conductors. Failure to comply with these requirements can lead to unequal current sharing, which can overload one or more of the conductors. When installing electrical services, it's important to consider the future needs of the building. As electrical loads increase over time, it may be necessary to upgrade the service to accommodate the additional demand. It's generally a good practice to size the service conductors and equipment to allow for future expansion. This can help avoid costly upgrades later on. Proper grounding and bonding are also essential for electrical safety. The grounding system provides a low impedance path for fault current to return to the source, which helps to trip the overcurrent protection device and clear the fault. The bonding system ensures that all metal parts of the electrical system are electrically connected, which helps to prevent shock hazards. The National Electrical Code contains detailed requirements for grounding and bonding, which must be followed carefully. When working with aluminum conductors, it's important to use appropriate connectors and termination methods. Aluminum conductors are more susceptible to oxidation than copper conductors, which can lead to increased resistance and overheating. To prevent this, it's necessary to use connectors that are specifically designed for use with aluminum conductors and to apply an antioxidant compound to the conductor before making the connection. Regularly inspect electrical systems to identify and correct any potential problems. Look for signs of overheating, such as discolored insulation or melted connectors. Also, check for loose connections and damaged wiring. Addressing these issues promptly can help prevent electrical fires and other hazards. Finally, always remember that electrical work can be dangerous. If you are not qualified to perform electrical work, it's best to hire a licensed electrician. A qualified electrician has the knowledge, skills, and experience to perform electrical work safely and in compliance with the applicable codes and standards. Understanding conductor ampacity involves understanding ampacity correction and adjustment factors. The ampacity of a conductor, which is the maximum current it can carry continuously without exceeding its temperature rating, is based on specific conditions such as ambient temperature and the number of current-carrying conductors in a raceway or cable. When these conditions deviate from the standard, correction and adjustment factors must be applied to the conductor's ampacity to ensure it is properly derated. Ambient temperature correction factors are used when the ambient temperature around the conductor exceeds 30 degrees Celsius (86 degrees Fahrenheit). Higher temperatures reduce the conductor's ability to dissipate heat, thus reducing its ampacity. Adjustment factors for the number of current-carrying conductors are used when multiple conductors are installed in the same raceway or cable. The heat generated by each conductor can raise the temperature inside the raceway or cable, which reduces the ampacity of all the conductors. The National Electrical Code provides tables that specify the correction and adjustment factors for various conditions. It is crucial to apply these factors correctly to ensure that conductors are not overloaded. For example, if you have 4 current-carrying conductors in a raceway and the ambient temperature is 40 degrees Celsius, you would need to apply both the adjustment factor for the number of conductors and the correction factor for the ambient temperature to determine the conductor's allowable ampacity. Conductor insulation types also play a significant role in determining ampacity. Different insulation materials have different temperature ratings, which affect the amount of current the conductor can carry. Common insulation types include THHN, THWN, and XHHW. THHN and THWN insulations are rated for 90 degrees Celsius in dry locations and 75 degrees Celsius in wet locations. XHHW insulation is rated for 90 degrees Celsius in both wet and dry locations. The higher the temperature rating of the insulation, the more current the conductor can carry. However, it is important to note that the termination temperature ratings of the equipment to which the conductors are connected must also be considered. Equipment is typically rated for 60 degrees Celsius or 75 degrees Celsius, and the conductor's ampacity must be based on the lowest temperature rating of the conductor, termination, or equipment. For example, if you are using THHN conductors that are rated for 90 degrees Celsius, but the equipment is rated for 75 degrees Celsius, you must choose the ampacity table for 75 degrees Celsius when determining the conductor size. This is to prevent overheating of the equipment terminations. Another important aspect of conductor sizing is understanding the difference between ampacity and allowable ampacity. Ampacity is the maximum current a conductor can carry under specific conditions, as determined by the National Electrical Code tables. Allowable ampacity is the ampacity after applying all applicable correction and adjustment factors. The allowable ampacity is the value that must be used when selecting the conductor size. To determine the allowable ampacity, you must first determine the conductor's ampacity from the appropriate table in the National Electrical Code. Then, you must apply any applicable correction and adjustment factors based on the ambient temperature, the number of current-carrying conductors, and other relevant conditions. The resulting value is the allowable ampacity, which must be equal to or greater than the load current. In addition to ampacity, it is also important to consider the conductor's voltage drop. Voltage drop is the decrease in voltage that occurs along the length of a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The National Electrical Code recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. To calculate voltage drop, you can use the following formula: voltage drop equals 2xkxixd/cm, where k is the direct current constant, which is approximately 12.9 ohms for copper and 21.2 ohms for aluminum. I is the current in amps, d is the one-way distance in feet, and cm is the circular mils of the conductor. The circular mils of a conductor can be found in the National Electrical Code tables. If the calculated voltage drop exceeds the recommended limits, you must increase the conductor size to reduce the resistance and lower the voltage drop. It's also crucial to understand the different types of electrical loads and how they affect conductor sizing. Electrical loads can be broadly classified into two categories: resistive loads and reactive loads. Resistive loads, such as incandescent lighting and electric heaters, have a power factor of 1.0, which means that the voltage and current are in phase. Reactive loads, such as motors and transformers, have a power factor of less than 1.0, which means that the voltage and current are out of phase. The power factor is the ratio of real power to apparent power. Real power is the power that is actually used to do work, while apparent power is the product of voltage and current. The lower the power factor, the more current is required to deliver the same amount of real power. When sizing conductors for reactive loads, it is important to consider the power factor. The National Electrical Code requires that conductors be sized to carry at least 125% of the motor's full load current. This is to account for the motor's inrush current, which is the high current that flows when the motor is first started. The National Electrical Code also requires that conductors be sized to carry at least 125% of the transformer's rated current. This is to account for the transformer's losses. In addition to the National Electrical Code, there may be local codes and regulations that also apply to electrical installations. It is important to check with the local authorities to ensure that all installations comply with these codes and regulations. Local codes and regulations may be more restrictive than the National Electrical Code in some cases. For example, some local codes may require larger conductor sizes or more stringent grounding requirements. Finally, it is important to document all electrical work that is performed. This documentation should include the conductor sizes, the ampacities, the voltage drops, and any other relevant information. This documentation can be helpful for future maintenance and troubleshooting. It can also be used to demonstrate compliance with the National Electrical Code and other applicable codes and regulations. In the context of the original question, the specific concern revolves around the potential misapplication of Article 310.15b6 to a situation involving paralleled conductors and an undersized neutral. The misconception arises from the idea that the ampacity reductions allowed by this article can be indiscriminately applied without considering other critical factors such as neutral sizing and the specific requirements for paralleled conductors. It's important to reiterate that Article 310.15b6 is primarily intended for service entrance conductors and dwelling units, and its application is subject to specific conditions and limitations. It does not provide a blanket exemption from the general requirements for conductor sizing and neutral sizing. When conductors are run in parallel, each conductor must be sized to carry its proportionate share of the total load, and the neutral conductor must be sized to carry the maximum unbalanced load, taking into account any harmonic currents that may be present. The use of a 4/0 neutral with parallel 350 aluminum conductors on a 300 amp service is highly unlikely to meet these requirements and could pose a significant safety hazard. In addition to the technical aspects of conductor sizing and neutral sizing, it is also important to consider the practical aspects of electrical installations. This includes factors such as the ease of installation, the availability of materials, and the cost of the installation. While it may be tempting to use smaller conductors to save money, it is important to remember that safety should always be the top priority. Undersized conductors can overheat, causing insulation damage, fires, and other hazards. It is always better to err on the side of caution and use conductors that are sized appropriately for the load. Furthermore, it is important to use high-quality materials and to follow all manufacturers' instructions when installing electrical equipment. This will help to ensure that the installation is safe and reliable. The selection of overcurrent protection devices is also a critical aspect of electrical safety. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect conductors from overloads and short circuits. It is important to select overcurrent protection devices that are properly sized for the conductors they are protecting. The National Electrical Code provides specific requirements for overcurrent protection, which must be followed carefully. In general, the overcurrent protection device should have an ampacity that is no greater than the allowable ampacity of the conductor. However, there are some exceptions to this rule. For example, the National Electrical Code allows for the use of the next higher standard overcurrent protection device in some cases, but only under specific conditions. In addition to protecting conductors from overloads and short circuits, overcurrent protection devices also provide protection against ground faults. A ground fault is a type of short circuit that occurs when a current-carrying conductor comes into contact with a grounded surface. Ground faults can be very dangerous, as they can cause electrical shock and fires. Ground fault circuit interrupters, or GFCIs, are special types of overcurrent protection devices that are designed to protect against ground fault. GFCIs are required in many areas of the home, such as bathrooms, kitchens, and outdoor receptacles. They work by monitoring the current flowing in the circuit and tripping the circuit breaker if they detect a ground fault. In summary, the proper sizing of conductors and the selection of overcurrent protection devices are essential for electrical safety. It is important to follow the National Electrical Code and other applicable codes and regulations to ensure that all electrical installations are safe and reliable. If you are not qualified to perform electrical work, it is best to hire a licensed electrician.